now that we've introduced vectors in two-dimensional space, let's talk about three-dimensional space. Now we have a few different names for three-dimensional space. Sometimes we just call it 3D space. Sometimes we'll call it 3-space. In math, we'll often notate it as R3. Blackboard, bold R with a 3 on top. Similar to how we notated two-dimensional space with R2, right? So first off, how does the coordinate system in three-dimensional space work? So we are going to take our two-dimensional space and extend it to 3 dimensions. Okay? So let's start with our two-dimensional space. So here's our x-axis, here's our y-axis. Notice I've only drawn the positive portion of the axes. It's going to be a little easier to keep track of them, but the negative parts of these axes still exist. Okay? So traditionally, how we represent two-dimensional space is we take these 2 dimensions and we imagine they are on a piece of paper. Okay? And then we imagine that piece of paper is lying flat. That's our x, that's our y. And then what we do is we add a third dimension coming straight up. And of course, if your first 2 dimensions are represented with variables x and y, your third dimension is represented with variable z. Okay? Now, this is great, except the y-axis is pointing away from us, right? Which means where x, y, and z are all positive is kind of not right in front of us. We would like the area where the x, y, and z axes are all positive to be right in front of us, easy to access. Okay? So what we do is we take this set of axes and we rotate it this way. Okay? And so after that rotation, what do we get? Let me kind of draw it there. We're going to rotate it 90 degrees this way. And so the x-axis is pointing this way. The y-axis is pointing this way. And the z-axis is pointing straight up. Okay? Now, this is a 3D this is a representation of 3D space, but projected onto 2 dimensions, right? So this is really a 2-dimensional picture, but it's representing 3D space. So this x-axis, if this were to be completely accurate, it wouldn't be kind of at an angle here. It'd be pointing directly out towards you, okay? So these are the positive axes. There are negative axes again. They would be just down this way, and down this way. In 3-dimensional space, we usually only draw the positive axes. If we draw the negative parts of the axes too, it gets a little busy. Okay? So when talking about like points in 2-dimensional space, we use ordered pairs. In 3-dimensional space, we would use an ordered triple. All right? So let's do a quick example so we could see what that looks like. Plot the point x, y, z equals 1, 3, 2. Okay? So x comes first, y comes second, and then the new variable z is will be the last number in the ordered triple. Okay? So I'm going to draw my axes real quick. So I've got my x-axis. Let me draw it a little bit bigger. I've got the room. X-axis. Y-axis. I'm sorry, not y-axis. That would be the z-axis. Y-axis is this way. Okay? So x, y, and z. And I want the point 1, 3, 2. So I'm going to add a few tick marks. 1, 2, 1, 2, 3, 1, 2. Okay? So 1, 3, 2. So 1 is right here on the x-axis, 2, or 3 on the y, 2 on the z, and I just want to get the point where those three meet up. Okay? Sometimes it's helpful to draw little dotted lines. It's a little more difficult to draw these in 3 dimensions than it is in 2, because again, we are projecting 3-dimensional space onto a 2D surface. Whereas when we were drawing with just 2 dimensions, our paper is a 2D surface, right? So I'm going to draw a little box to kind of help me see where this point would be. And we could see this point right here. That would be the point 1, 3, 2. Okay, it's 1 out on the x, it's 3 out on the y, it's 2 up on the z. Okay? Next, I want to look at the equations and graphs of simple surfaces in 3-dimensional space. Now, before we jump right in, I want to look at a simple example in 2D that will help us in 3D. Okay? So let's say I'm in 2D. Let's graph the equation y equals 2 in R2, 2-dimensional space. Okay? What would the graph look like? Well, we know what y has to be. Y has to be 2. But what about x? This equation is just telling me about y. There's no restriction on x. So x could be anything. So I find the level at which y is 2. And then that y could be any value here, or that line, the equation, is all values along this line, because any value on that line has y equal to 2. X changes, but the y is always 2, and that's what the equation is saying. So this line is the graphical representation of y equals 2. Okay? Now let's see what that would look like in 3 dimensions. Let's graph y equals 2 in 3 dimensions. The idea is very similar, but now we're going to do it in 3 dimensions. Okay? So let's get an x-axis, a y-axis, a z-axis. Okay? We know that y has to be 2. That's the restriction that the equation is telling us. But it has no information on x or z, which means x and z, they could be anything. Which means that I'm going to find where y is 2 on this axis. Okay? That's where y is 2 on the y-axis. But this isn't just the point on the y-axis, it's all the points where y is 2. So I could have any z, any x, so long as y is 2. So I'm going to end up getting a plane. An infinitely wide, flat surface like this. It goes through this point, y equals 2, but it has all the other points where y is 2 also, for any x or any z. Okay, it stretches out infinitely far in all directions. Notice I do have boundaries here. Those boundaries are just because I can't draw an infinite plane. I have only a finite amount of space, right? So it's an approximation, all right? So that's what the graph of y equals 2 would look like in 3 dimensions. All right, let's do one more. Let's graph x equals 2z squared. Okay? Now looking at this equation, it involves x and z, but it doesn't involve y at all. So whatever's happening, y could be anything. So we really have to figure out what the x and z are doing. Once we figure out what x and z are doing, the y can be anything. Okay? So what I'm going to do, I want to sketch this in 3 dimensions, but I'm not going to do it right away. Since the y can be anything, I'm going to focus on just the xz plane. The xz plane is the plane that intersects the x and z axes. Let me do it this way. There we go. Okay. So it's this plane here. So I'm going to focus on just that plane. So I'm going to kind of even take that plane and separate it. So here's my x-axis, positive x-axis. Here's the positive z-axis. What would x equals 2z squared look like? Probably extend this a little. Okay. Hey, I know what that is. That, if I forget about the fact that the variables are a little strange, it's a parabola, right? And in the xz plane, this would be a sideways parabola because the z is squared, the x is not. Its vertex is at the origin, and it's going to open in the positive x-axis. Okay, so if I go up 1 or down 1, it's going to go out 2 units. Okay? That's what this graph looks like, restricted to just the 2-dimensional space of the xz plane. Now let's take that and extend it to full 3-dimensional space by stretching it out along the y-axis. Okay? So in the xz plane, now I kind of have to translate this over here to the xz plane because the positive x-axis is pointing this way, positive z-axis is up here. And so I'd get something like this. So vertex at the origin, if I go up 1 or down 1, I'd go over 2. So I'd go out this way to about there, right? And then this way to about there. And so with the perspective, this is kind of like what my parabola looks like. Sketching in 3 dimensions is harder than 2 dimensions. Again, we're projecting 3-dimensional space into 2 dimensions. Okay, so that's taking just this image onto this xz plane. Okay, but remember, no information about y. So this same image stretches for all possible y values. Okay, so for this y, hey, guess what? I get the exact same image because x and z are doing the same thing at this value of y. Okay, so I get, I don't know if I want to try to sketch it out. Maybe I will. Right about there. And this one right about there. Okay? And again, this is going to happen for any y value. So I've given you an example of 2, but it happens for all of them. So what we get is a surface. Do it this way. There we go. We get this surface. Okay, and I've drawn just a portion of it along the positive y-axis, but it extends infinitely far in this direction, in this direction. Okay, and it's this parabola shape stretched infinitely far with the mouth opening towards you. Okay, it'll help if you could see a 3D demonstration of it in a graphing utility. So let's take this and do the same thing. X equals 2z squared. Okay, change the color to match. Let's take out that xy plane. It's kind of in the way. Okay, so notice if I restrict myself to the xz plane, I get that parabola, that same parabola. Okay, but with the y, that parabola stretches in that y direction. And I get that structure that I drew. Okay? And I want to emphasize this drawing, it's not meant to be perfect. I don't expect you to draw it perfectly. It's meant to communicate an idea. Okay? And most importantly, to communicate the idea into your own mind. If you want to really draw this shape so that other people can understand it, well, the 3D graphing calculator can do it better. But while you're drawing this, you'll understand what's happening. What is this shape giving you? Okay? We call a shape like this, we call a surface like this, a cylindrical surface, because it stretches, it keeps the same basic shape, but stretches infinitely far in one direction. In fact, we can use this idea to sketch a cylinder. Let's graph. Let's graph x squared plus y squared equals 4. Let's do it in 3-dimensional space. Okay? So just as before, this only mentions 2 variables. When you have an equation that only mentions 2 variables and you're graphing it in 3-dimensional space, you are going to get this cylindrical surface. Whatever is happening in the xy plane, or in the plane of whatever 2 variables you're working with, stretches infinitely far along that 3rd variable. Okay? So in this case, x squared plus y squared equals 4. Hey, that just, in R2, that's just the xy plane, where we know that. It's a circle centered at the origin with radius, radius squared is 4, so the radius is 2. So I'd go 2 out in each direction. 2, 2, 2, 2 from the center. Okay, that's what this circle looks like in the xy plane. But now I want to stretch it infinitely far along the z-axis. Okay? So in 3-dimensional space, we take that structure from 2-dimensional space, which would be the xy plane, which would be this plane laying flat right here. Right, where the x and y axes go through. And I draw the circle going through those points. A little bit tricky because it's laying flat, right? Okay, so that's the circle laying flat. But then there's no mention of z. And so I stretch it infinitely far in the z direction, up and down. and I get a cylinder. That's why we call these cylindrical surfaces, because a cylinder is kind of the classical example of one of these kinds of surfaces. Okay. Again, let's take this to Desmos. My picture here, kind of hideous, isn't it? Okay. Again, it's not meant to be perfect. It's meant to help you understand. It's a tool to help you understand what the surface is. Once you have a basic idea of the behavior of the surface in your mind, you don't need the picture anymore. The real object is to get it into your mind. Okay. So let's get Desmos back up here. And let's plot this surface. Okay, so notice in Desmos, when you're only using X and Y, it will restrict your graph to the XY plane. So I get that circle that I was expecting. Okay, but it has this little checkbox that I can extend it to full three-dimensional space. So let's see what happens when I extend it to full 3D space. And look at that. I get a cylinder, which is exactly what I expected. Okay, that circle extends along the z-axis because there are no restrictions in the z direction. There are no restrictions for the z variable. One of the best known formulas in two-dimensional space is the Pythagorean theorem, which of course relates the sides of a triangle. A squared plus b squared equals c squared. And we can use this as to find the distance between 2 points. Okay, if I have 1 point, x1, y1, and another point, x2, y2, I can find the distance between these 2 points by thinking about it as a triangle. Right? The change in x, I'm going from x1 to x2, so the change is x2 minus x1. The change in y, I'm going from y1 to y2, so that's y2 minus y1, which means my distance, well, the distance squared would be x2 minus x1 squared plus y2 minus y1 squared, using the Pythagorean theorem. And so if I want my distance, which I know is a positive quantity, it'd be the square root of that. So that's the distance formula. It's really just an application of the Pythagorean theorem. What we would like to do is we would like to find an equivalent formula in 3 dimensions, an analog to the Pythagorean theorem in 3 dimensions. Okay? So we're going to think about this. I'm going to draw a 3-dimensional space. X-axis, y-axis, z-axis. Let's take an arbitrary point in 3-dimensional space at point x, y, z. Okay? And we want some analog of the Pythagorean theorem. So let's do it this way. I'm going to start by thinking about this much how we did in 2-dimensional space. I'm going to draw a right triangle like that. Okay, so this is a right triangle. It's in perspective, which is why that angle doesn't look right, but it's in perspective. It's a right triangle. Okay. Notice I know how high up this triangle is. I know the length of this side because it should be right about there, which is how tall the point is, right? It should be the z coordinate. And I want to find, let's give a value to this. Let's call it d. Okay, this is what I want. So I know this side. If I could find this side, then I could just use the Pythagorean theorem as normal, right? So the trick here is to draw another triangle. another triangle over to the x-axis. This is another right triangle. And so between these two triangles, I can figure out what I want, because now this edge of this triangle is an x. That's how far it goes out, right? This x, the x of the point. And this edge, well, that's just how far out it is on the y-axis. So it goes out y units. And because this is a right triangle, I can use the Pythagorean theorem on the green triangle here to find this edge, the length of that edge. Okay? So this edge here, maybe I should, let's give it a name. I'm going to call it R. Okay? So if we're going to find R, by the Pythagorean theorem, r squared is equal to x squared plus y squared, just looking at that green triangle, right? And since it's a distance, r is going to be equal to the square root of x squared plus y squared. Okay? So that's for r there. But now that we know this edge here, we can use the Pythagorean theorem on the yellow triangle. The standard two-dimensional Pythagorean theorem on the yellow triangle to figure out what that d is. Okay? So with the yellow triangle here, we would have d squared equals r squared plus z squared. If I plug in my r is equal to the square root of x squared plus y squared. R squared is just equal to x squared plus y squared. So let's take that and plug it in. Okay? And that means d squared is equal to, swap out r squared for x squared plus y squared, plus z squared. I could drop the parentheses. And my goodness, the three-dimensional Pythagorean theorem is real easy, right? For 2 dimensions, it's just the squares of the two sides. For 3 dimensions, you just throw in that third coordinate, okay? This side would be just the sum of the squares of these two sides. In 3 dimensions, you have a third coordinate, so you just add that sum of the square of the third coordinate in. It really is that easy. 3D analog of the Pythagorean theorem. The distance of a point xyz to the origin is given by d equals square root of x squared plus y squared plus z squared. Okay? And we could easily use that to find a general distance formula in 3-dimensional space. Not just the distance of a point to the origin, but the distance between any 2 points. If I have, you know what, I'm not going to draw it. I think the picture would be confusing. But the distance in 3-dimensional space, the distance from x1, y1, z1 to x2, y2, z2 is, well, I need to find how far I travel in the x direction. So to go from x1 to x2, the distance between the x's, you just subtract them. Okay? So that's the change of x plus how much I change in the y direction. So if I go from y1 to y2, how far I've traveled is just the difference of them. Okay, so change of y squared plus change of z squared. If I'm going from z1 to z2, the amount that I've changed in the z direction is just how the difference of them, subtract them. So that's the change in z squared. This is the general distance formula between 2 points in 3 dimensions. Okay. Now we're restricting ourselves to 3 dimensions here, and in this class we won't go further. But you could actually extrapolate this and see what would happen in 4 dimensions or 5 dimensions, even though we can't draw it. Okay. The distance formula, or the equivalent of the Pythagorean theorem in 4 dimensions, you just add that 4th variable squared. It's that simple. Okay? We could use this to derive a formula for the equation of a sphere, because a sphere is all the points a set distance away from a predetermined center. Right? All the points a set distance away in 3-dimensional space from a center. So if I think about a sphere, let's get a predetermined center. Let's call this center x naught, y naught, z naught. That's my center. I want all the points a certain distance away from that center. Okay, we'll call the distance the radius, of course. And if I take any point x, y, z on the edge of the sphere, it should be a distance r away from the center. And so the distance between this point and this point should be r. So the distance, using the distance formula, we get x minus x naught squared plus y minus y naught squared plus z minus z naught squared. Take the square root of all that, it should be the predetermined distance from the center, r. And if we square both sides of the equation, then we get the standard form of a sphere. Or the equation of a sphere in standard form. Let me put it that way. X minus x naught squared plus y minus y naught squared plus z minus z naught squared equals r squared, where the center of the sphere is x naught, y naught, z naught, and the radius of the sphere is r. Now let's talk about vectors in 3 dimensions. Vectors in 3 dimensions are exactly like vectors in 2 dimensions. It's one of the advantages of vectors, is no matter how many dimensions you're dealing with, they behave exactly the same. A vector is a quantity with direction and magnitude. But again, not position. You draw a vector with the same direction, with the same magnitude, in 2 different locations, it is the same vector. Okay? But now, of course, we're dealing in 3 dimensions. And so there's just more places, more directions for it to point. Right? We still represent vectors in 3 dimensions with arrows, though it's a little harder to visualize it unless you can rotate the image. We still represent vectors either in component form using those angle brackets. So for example, I might have 2, -3, 4 for a vector pointing in that direction with a certain magnitude, right? Or I can write it in terms of the standard unit vectors. And here we use I and j just like before. I is the unit vector pointing down the x-axis. J is the unit vector pointing in the direction of the positive y-axis. And then we need one more vector because we have an additional dimension, right? So we let vector k be the unit vector pointing down the positive z-axis. Okay? So we'd have these three vectors, I, j, and then let me draw j a little further this way, j, and then k is pointing straight up down the positive z-axis. Okay? Vector operations are exactly as before. Scalar multiplication stretches out the vectors. So if I have a vector v in 3 dimensions, let's give a specific example. 1, 2, -3. And let's get one more. Vector u, 2, -4, 1. Okay. If I do 3 times v, that just multiplies each component of v by 3. 3, 6, -9. And now this vector is 3 times as long as before. 3 times as long as v, but it's pointing in exactly the same direction, right? I could add 2 vectors together, just as before. As before, you just add the corresponding components. So 1 plus 2 is 3. 2 plus -4 is -2. And -3 plus 1 is also -2. Okay? The interpretation of vector addition is exactly like it was before. If I have 2 vectors u and v, which I'm not necessarily drawing the same way these would be drawn. Okay, u plus v, get something a little more distinct. U plus v could be interpreted this way. Okay, using this triangle approach. U plus v is the vector pointing to where you would end up if first you travel in direction u and then travel in direction v. Okay, subtraction works exactly the same way. So let's so this was v plus u. Let's do v minus u. And you would just subtract corresponding components. You just have one more component to work with, right? 1 minus 2 is -1. 2 minus -4 is 6. And the last component, -3 minus 1, is -4. Okay? Subtraction, you interpret it also the exact same way. For vector subtraction, if I have 2 vectors u and v, then if I subtract them, I would get a vector pointing from the end minus start. Okay, if I subtract 2 vectors, I get a vector pointing. In this case, I'm doing v. If I do v minus u, I end up at v, end, and I start at the tip of u. Start, so end minus start. Okay? And just like in 2 dimensions, I could use this to find a vector pointing from one point to another. Okay, so let's do a quick example with that. Find the vector that points from point P, 1, -2, 1, to point Q. 3, 1, negative 4. Okay? So I could plot those in three-dimensional space if I wanted. But, well, let's go ahead and do it. X, Y, Z. So P is at 1, negative 2, 1. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. P is at 1, negative 2, 1. So 1 out on the X. 1, 2 on the Y, and 1 up. Okay. So this point here, that would be point P. Q is 3, 1, negative 4. So I'd go 3 out on the X. 1, 2, maybe use a different color here. 1, 2, 3. 1 out on the Y. 1. And negative 4 on the Z, so I go down 4. 1, 2, 3, 4. So let me scroll down a little bit. It'd be right about here. Okay? I want the vector pointing from P to Q. The way I could do this is I could think about the vectors pointing to P and pointing to Q from the origin. So if I think about this vector, I'll call it vector P. If I think about this vector, I'll call it vector Q. Then this vector here that I want, the vector points from P to Q. Well, I want to start here. I want to end here. If I want a vector that goes from a start to an end, I could do end minus start vector subtraction. Okay? So I'm going to do vector Q, the vector that points to Q, minus vector P, the vector that points to P. Because both of these vectors are in standard position with their tails at the origin, vector Q and P are just the vectors with these same components as the points. Okay, so vector Q, 3, 1, negative 4. That would be the vector that gets me from the origin to Q. Okay. Subtract vector P, same components as point P. 1, negative 2, 1. That's the vector that takes me from the origin to P. Subtract corresponding components. 3 minus 1 is 2. 1 minus negative 2 is 3. Negative 4 minus 1 is negative 5. And that is the vector PQ, the vector that points from point P to point Q. In 2 dimensions, we learned how to isolate the magnitude of a vector and how to isolate the direction of a vector and keep them separate. It's pretty much the same thing in 3 dimensions. Okay? So remember, we can find the length of a vector by taking its norm. Norm of a vector. So for example, if v is equal to 3i plus 2j minus k, I could find the norm of v, that is the length of v, the magnitude of v, using the 3-dimensional analog of the Pythagorean theorem, right? I just want to find the length of this vector. If I were to plot the vector in 3 dimensions, it would be where? 3 out on the x, 1, 2, 3 out on the x, 2 out on the y, 1, 2, 1 down on the z, be about there. if I think about the vector that points to that, that's the vector I want, right? Vector that points from the origin to that point. So if I could find how far this point is from the origin, that would also tell me how long the vector is. Okay? So I just use the distance formula, or the three-dimensional analog of the Pythagorean theorem. Okay? It would be the square root of the first component squared plus the second component squared plus the third component squared. Okay, that's the general formula for finding the norm of a three-dimensional vector. You take the sum of the squares of the components and square root them. In this case, what do we get? We get 9 plus 4 is 13 plus 1 is 14. The length of this vector is square root of 14. Okay? Similarly, we can isolate the direction of the vector. We can focus on the direction of the vector by normalizing the vector. That turns it into a unit vector, a vector of length 1. Okay? To normalize a vector, we take the vector, just like in 2 dimensions, we take the vector and then we divide it by the norm of that vector. Okay? Or you could think about it as the vector and then we scalar multiply by 1 over the norm of the vector, depending on how you want to think about it. Okay? It's really a scalar multiplication operation, but when we divide by a scalar, we could think about it as multiplying by 1 over that scalar. Okay? So in this case, let's use the same vector v. We've already found the norm at square root of 14. So I'm going to take that vector v, that's 3i plus 2j minus k. 3i plus 2j minus k. And I just divide each component by the square root of 14. My resultant vector is 3 over root 14i plus 2 over root 14j minus 1 over root 14k. This vector points the same direction as the original vector v, pointing in exactly the same direction, but now it's a unit vector. Meaning it has length 1. The magnitude of this vector is 1. A unit length.